Good evening, welcome everybody. This is Obi-Wan Pez for N Simplex Pachinko. We're starting a bit late tonight, sorry about that, but we'll see what's going on. We'll see who's got questions. And see what anybody might be interested in. So, tonight, we're also going to look a little bit at curriculum, which we have here. Flashbang. Ow. Oi. Alright, hang on. Decided it didn't want me to have that one on. Sure, why not? Okay. Getting a little bit to where we were. All right. That's right. I don't want that one actually. Where I want to go is to my Obi account and get to Hey, famished. Yep. So we're looking at absolute value functions. Okay, so we're looking at the absolute value functions. Talked about how they are specifically distances, right? How do they create the parent function? What is the absolute value of x? What does it mean? Going to go through the basic properties of the function itself. So what are domain and range, extrema, graphs, intercepts, etc.? How can we express this thing in terms of like all the different function properties we were talking about before? Right, that includes symmetry, that includes start precalculus in second. Nice. When does that actually start? We do the function transformation stuff that we talked about above, where we look at all of the possible ways we can linearly transform an absolute value function.
Always on the lookout for new tunes? Spotify Premium lets you explore a catalog of millions of songs with high-quality audio. Get 3 free months now and cancel anytime.
Then we do algebraic manipulation. So we have my pseudo-graphical distance method that we always talk about here on this channel. When to take it or how much to do? Yeah, well. Is it self-paced? And then we get the definitional algebraic method. So we specifically talk about the or nature of the absolute value function. So it means that when you have a number that is a positive value or a distance between the two objects that is a positive value, then you just take the function itself. The value that you plug in is the value that you come out with. And if you have a negative value that you started with, then you take the opposite of that, which ends up being a positive value as well. Self-paced, yep. Yeah. Don't burn yourself out too much, though. Okay. What do they mean? I'm not even sure necessarily that I have a very good idea of what I'm doing here in terms of like, what does it mean? Like I just feel like that is something that we need to talk about sometimes, And I mentioned it when we were talking about just functions generally, so like it would help if we could individually talk about that in terms of each individual section. Make sure that we actually get those values in. I need to buy more light bulbs tomorrow. And then what applications do they have is going to be a fairly important thing no matter what section we're talking about. So in here, we're going to talk about computer programming tolerances in terms of absolute values. Boy. It's 11 o'clock. Okay. Alright, so once we get talking about absolute value functions, we get done with that stuff. Then we come in here and we say this is what we're doing here. This is day, I don't know, 6, I think. Yeah. Okay, so 1. Etymology, history. So break down the word itself, polynomial, poly meaning many, nomial meaning like names or terms or things like that. And then we talk about the history of polynomials. So when we start talking about polynomials themselves, it's going to be in terms of the mostly Arab world, where there were other civilizations that also had their own. So the Indian and Chinese civilizations worked with polynomials somewhat. But again, like formalization ends up being kind of king for this. So the Greeks did work on polynomial equations, trying to solve things that are squares. We have Diophantus, who came up with a whole bunch. That's really going to piss me off in a minute here. I really should not replace that, like, on stream. Probably just a bad idea. Okay, so what happened here? Okay. So we have like measurement of areas just kind of generally. It was showing us that we needed to be able to figure out what the size of a region was, and trying to prove sizes of regions was getting to be difficult in terms of like just using, you know, squares of a certain size and then trying to, you know, overlay them onto a grid or anything like that. It just never quite worked out. Alright, so we're looking for the measurement of areas, especially squares. We're kind of where the parent functions come from, so this is y equals x squared. What are their above properties? So we need to go back to the other one and say, yeah, that's cute. What are the properties we're looking for? Domain range, external graphs, intercepts, etc. We'll hang on to that one. So to do the linear function transformation, we're going to show that A and B be combined. So this is our vertical stretch factor and our horizontal compression factor. If you have a B on the inside of those parentheses with the square, then you can factor it out, square the thing, and then take it out and make it part of A instead. Similarly, if you feel like having a horizontal compression instead of a vertical stretch, then you can reverse that and take a factor off of A that is a perfect square, preferably, and then bring it inside the parentheses and make it a little bit easier to work with. Doesn't always work, but, you know, I find it interesting. And at the very least, an interesting idea that students might be able to use. How do we manipulate them algebraically? So in this case, we want to find we're going to use find the intercepts based on transformation form, which ends up being real easy. Okay, and explain why standard form is a terrible term. You should not use it. Ever. Those of you who are teaching, don't use standard form. Right, so we're going to do the basic definition of polynomials first, then we get into the higher order polynomials, you know, the specifics of it, the etymology, the history, and all that stuff. I mean, apart from etymology. That's about it. So higher order stuff we do as a part of later sections. Right, not exactly. Not exactly the same, but that's higher order polynomials. Right. Development proof of existence. This gets a little interesting because we have the European math duels are something that definitely need to be brought up every time. Create the parent functions. This is going to be we can do a multinomial expansion if we want to. No, that's going to be in algebraic. General polynomial form. In this case, we can do our multinomial expansion. And connect the idea back to the simplex. Okay. And let's see. This is the right, the volume taken up by water at certain temperatures actually ends up changing ever so slightly, just based on the amount of energy that is in the atoms that are bouncing around. So if you have a lot of energy, i.e. it's close to boiling, then it takes up a lot more space overall, right? Some of it is, this is before it starts boiling off, going through phase change. So it'll still have a higher volume at a large temperature, or high temperature that is below 100 degrees Celsius. because all of the atoms are bouncing around off of each other, and with more energy they end up bouncing more, which means that the substance itself takes up more space, if only ever so slightly. As water loses heat and drops in temperature, then we see that all of those atoms start calming down a little bit, and they bounce around less and more slowly, and they interact with each other, again, on a much smaller scale. Eventually, this actually reaches a minimum, which is a little weird. So it'll reach a minimum value. I forget exactly what it is, but it's like 5 degrees Celsius or something like that, where water takes up the least amount of space. And then as soon as you start dropping the temperature more than that, to like 2 or 1 degree Celsius, the instabilities in overall temperature end up meaning that like some parts of the water are becoming, I hate to say slightly more crystallized, but they're like moving into arrangement to start the crystallization process. And so they end up taking up more space again before they freeze. Ever so slightly before they freeze, but still before they freeze. They take up more space because the atoms are starting to arrange themselves into a ice crystalline lattice. It's really cool. That's also why when you put like a water bottle in the freezer, if you manage to let it actually freeze, then it ends up taking more space and can end up bursting whatever container you have. If it's something like your wonderful Nalgene bottle, I did not, but somebody else did. It ended up along the seam where the two halves of the curve ended up meeting. It ended up pulling apart like this, just ever so slightly sheared, because of the pressure on the inside of the water ending up like pulling apart the two parts that were connected. It was wild. It didn't quite break, but it stretched the plastic so much that it basically became almost non-functional. So volume of water at certain temperatures is going to have a polynomial behavior. Higher degree, non-quadratic. We also have something with electricity and magnetism. I don't remember what it is now, but yeah, finance, electronics. I mean, obviously, any sort of curve fitting. That's kind of cheating to call it that. Oh, interpolation. We could use this for like also computer graphics. These are all quadratic. It's not very helpful. These are all quadratics. Again, all quadratics. Right, computer graphics, polynomials are important for making lifelike 3D objects. Smooth shapes. Oh, that's right. Image processing. So if you were to do some interpolation on a particular picture, so if you're often whatever your photo manipulation software is, you can zoom in on a certain area and use a polynomial transformation in order to make the area become more smoothly colored instead of being more pixelated. So may not be perfect, but you know, somewhat works. Data compression. Error correction, yeah. Error correction algorithms. And signal processing. Good times. Great. So with both of these, we're going to want factoring. applications of quadratics. We've got a lot of stuff. So, projectile motion, areas, pretty much anything you want to talk about when it has an area. Thank you very much for the follow. So projectile motion areas. There's also like we did a project. It was a very small. I mean, it wasn't really a project, but we were dealing with like supply demand functions where we were doing like economic principles. What would be the maximum profit if when your management consultant says, hey, every time that you raise the price by 5 cents on grapes or something like that, then people will buy on average a pound less. So you work out, or per month or something like that, and you can work out based on that information only. Then you can mess around a little bit and figure out eventually what the predicted function is going to be for supply demand, and then I guess price demand function, and then figure out what the maximum is going to be, figure out what the maximum profit's going to be by subtracting the cost. There's all sorts of fun stuff you can do with that. Hey, patient. Good evening and welcome. So, a little bit of both. It kind of depends. I'm a big fan of a lot of the stuff that I teach, and so like if I have taught it, then I have had to grapple with it and really understand what's going on with it. I like giving students a reason to do particular problems and things like that, but it's not like absolutely necessary for me to say like, you have to have an application, or you don't ever need an application. I like working out the pure reasons why things work. Students don't care, almost ever. The ones who do are usually the ones who are going on to science programs somewhere. So once we start getting into a particular topic, and if they're going to start asking about like, well, how does this actually work, or how does it affect things, then I know that we've got some interesting conversations ahead. Let's see. Okay. Still got about 10 more minutes or so until the next ad break. So, just letting people know. Okay. Well, thank you. It's getting a little bit long, but normally I probably got another month or so. But oftentimes by now I'm cutting it down to went to the guys over at the barber shop and was like, all right, look, I'm an American. It's going to be super easy. Ready? 2, 4, 6. Go. Just take the attachment, clip it in, just do all that, and then clean it up with a razor. You're good. Most of the time, I don't want to spend 3 hours in a chair. It's not going to be 3 hours, but better part of an hour in the chair. It's like, let's just move. You can move on to another customer. I think I left my... Yeah, I'll have to show you. So, my name, Obi-Wan Pez, comes from... comes from how I look. One of my friends found a Pez dispenser of Obi-Wan Kenobi from the Clone Wars series when that was coming out in, God, 2006, something like that, 2008. And she was shocked by walking through this particular store that there was an entire end cap where just my face was staring back at her, 50 times over. So it was fairly shortly after that I developed this online persona. That's not true. It was more like 2014, 2015 when I developed this online persona and said that's going to be my actual username that has A, nothing to do with my real name, and B, unlike some of my other, whatever accounts I had way back when, and like is unlikely that anyone else would ever pick anything similar. I was really into Les Mis, but picking Valjean _24601 probably was going to be taken many times over. All right. So, patient, if you have any questions, let me know. My specialties, generally speaking, are algebraic subjects that range from pre-calc on one side all the way up through differential equations. Those are the ones that I had to run the course and manage all of the other adjunct professors and even the full-time people who were teaching it. Like, we'd sit down and have conversations about kind of what my vision was in terms of how to teach these things and possible ideas for them to research in terms of, like, my particular bend often ended up being math history. So I would talk a lot about ancient civilizations, working on through to modern times, and who did stuff in each of those sectors. I don't know if my co-conspirator back in my community college is still doing any of that, but she and I were co-coordinating the Precalculus program just before I left. So I handed it off to her and said, good luck. Okay. I say day 7. It could be day 8 pretty easily. Polynomials, generally speaking, have all sorts of good stuff. Let's see, factoring. We also need to deal with solutions, unexpected solutions. Right, so here we're going to have to talk about set theory and complex numbers. Do we do that before or after factoring? I think maybe after. There's arguments for both. Right, general solutions via the quadratic formula. Projectile motion, areas, economics. That's physics. This could be electricity as well. There's probably also higher order polynomials in there somewhere, but kinetic energy is another thing that oftentimes uses a quadratic somewhere inside of it. Oh, there's a fun one. Numberphile did an interesting question on kinetic energy, which was if you're driving down the road at 50 miles an hour and another car like passes you doing 100, and then at the exact same moment you both see that there is a tree across the road and you both slam on the brakes, you will both reduce the total amount of kinetic energy in your cars based on the braking motion and all this stuff. If you barely tap or like stop your car at the tree that had fallen across the road, how fast would the car going 100 when you were going 50 end up hitting the tree? Because they will hit the tree. And it's quite an interesting answer if you think about it from a kinetic energy perspective. Alright, famished. Good luck. Alright, ads are going to start in a minute, so I'm going to hit the button. Like reviewing every 2 to 3 weeks. Yeah. Doing digital notes is usually pretty good. I'm going to hit the button. I'm going to go downstairs, trade out some laundry, grab a drink, and cycle some water. So I will be back in 3 to 5 minutes. It depends on how much I have to actually wrestle with the laundry. So I'll be right back. Thank you so much, everybody, for coming, and see you in a little bit. Hey, welcome back. Being able to type out your notes will be beneficial. Yeah. I had to get the standing desk capability on this back and running again. It's been unplugged for, since we left America, because it's an American plug, and I do have a transformer that's here in order to plug in my computers and the power strip that it's all connected to. It turns out that it is vitally imperative to have transformers for like pretty much all of your electronics. Certain appliances and things like that, you can throw them into a universal power strip, but there is a potential problem in that some of the things that we plugged it into were not very universal. So I ended up we got a universal plug that I brought upstairs, and I took my radio alarm clock from the States and I plugged it into the thing, and every single one of the segments all lit up. I was like, that's not good. And then about 2 minutes later, when I went to go like actually change the time and things like that, it just went dead. And I'm like, all right, well, won't be doing that again. So some of the problem is that the UK works off of a 50 hertz system, So energy cycles through the alternating current that they have here at 50 times a second, and energy cycles through the US system at 60 hertz, or 60 times a second. Those two numbers are not the same. And so because you have, actually, this is a good example. Because you have these two electrical signals not lining up, right, we end up with this nonsense. So the difference between the two, if we say like in between -1 and +1, is what your electronics should be like capable of handling. You notice that here we get this out of phase wild electronic signal here, which will also cause, let's go with, go like that. Right, so normally you should either run your electronics at 50 hertz like this or at 60 hertz like this. It's not exactly true in terms of both what I'm saying and also how it exactly works with like the two systems. It's not quite the same as as this. I think I need a 2 pi stuck in there somewhere, but yeah, that's fine. Right, it's not going to change the overall fact of what's going on here. Again, UK system in red, US system in blue, and when you find the difference between these two things, we get this green system here. So the supply was supplying red, and the electronic device that I had, the radio alarm clock, was receiving green, essentially. So instead of having a voltage that was between -1 and 1, as in like 100%, that was cycling to both sides. Again, this is alternating current, so like the electrons are kind of moving back and forth as they're moving through the device. 50 times a second. It's expecting to receive 60 times a second, and so we get these beats where we get these values that get as high as 1.97, or 98% above what they're supposed to get, and down to same deal here, 98% higher than what they should be getting. So we're almost, but not quite, doubling like the electronic input to that device. So no wonder it shorted out. No wonder it didn't work anymore. Again, not quite how it works, but it's close enough. Tonight is #not sponsored by Lost and Grounded. Wanna go to the sun? Pale ale. like most pale ales, very hoppy. Okay, so go back to pre-calc curriculum. So the other things that we want to look at, right? We got the general solutions via the quadratic formula. Okay, we said we want to deal with factoring and how to find, that's trying to find intercepts. Alright, so this is the moment for Tartaglia, Cardano, and Ferrari. So there were European math duels for professorships. They wouldn't have any actual danger involved. It was just that certain individuals within the math community were very interested in gaining and then keeping their professorships because they were like not super cushy jobs, but certainly better than having to struggle as a freelance mathematician out in the regular world. Having a professorship at a giant university somewhere was going to guarantee you an almost lifetime of at least comfort. You would still have to teach classes and teach, do research and things like that. But if you wanted to, you could challenge any particular person and say, I'm going to challenge you to a math duel. And so the person in question would end up sending over a letter to a particular individual. That particular individual could then respond in the affirmative or like, yeah, no, we're not doing that. And the department would weigh in on their opinion. If a particular professor was, let's say, not pulling their weight around the department, it's very possible that they'd be like, no, you're doing it. We don't really want you around, so. So, Nicola Fontana, also known as Tartaglia, was a, I think, 12 or 13-year-old boy in his Italian village when a rampaging French army came and sacked the town in order to basically turn them into now a French-controlled region. So the Italians were like, yeah, no. And Tartaglia was manning, I don't know if it was like he was manning some sort of siege engine or, whatever it was that he was doing. The French cavalrymen rode up on his horse and slashed him with a saber and caught him in the neck. Luckily, did not bleed out, but he ended up chipping his larynx, and his voice box had some sort of nerve damage, so he wasn't able to speak 100% the same ever again in his life. He, in particular, had a bit of a stutter, and the kids in his town started making fun of him by calling him Tartaglia, which means the stutterer. And at some point, Nicola Fontana said, you know what, screw it, that's my name now. And he was now Nicola Tartaglia. So, over time, he gained some reputation, both as just general badass and as a decent mathematician. He was then able to secure a position at the local university and ended up working there for quite a while. So, the person that he had challenged to a math duel was also an expert of quadratic and cubic equations. Cubic equations at the time were kind of like the height of mathematical research, at least in pre-Renaissance Europe. This is around 1400s, 1450s, I think. And so Tartaglia went to his journal and started working on certain types of problems, and he was able to solve a few new types of cubic equations that people weren't able to solve, at least terribly easily. He got word that his opponent had also been doing some decent research and was able to figure out a lot of other cubic forms of equations, and he said, well, this is not going to end terribly well. I need to solve the general cubic polynomial equation. And so he right. And so Tartaglia, after some time, was able to come up with something that looked a bit like this. This is not exactly the same. Again, Cardano, who's somebody else, coming here in a little bit. Oh, 1500s. Nuts. Anyway, so Tartaglia allegedly came up with this formula, or something very similar to it, and was able to go to the math duel and answer every possible question that his opponent threw at him. And he was asked by numerous people if you wouldn't mind showing and sharing your cubic equation solution, and Tartaglia said, no, I'm going to use this. It's going to be my, essentially, like, it will be my key to holding on to this professorship position. And that was the end of it. It wasn't until, 1540s, essentially, that Cardano asked Tartaglia if he wouldn't mind sharing the formula, and please, wouldn't he allow him to work on it? And Tartaglia said no, but eventually relented and said, okay, fine. As long as you never publish it yourself. And Cardano was like, yeah, I mean, all right. You could see that there's a problem here. Given that this says right here, right, Cardano published this in 1545. Because the problem was that he had a brilliant student himself. Cardano had a brilliant student who came up with, by himself, not only the solution to the cubic equation, but also the solution to the quartic equation. There was a general solution to the quartic equation, which also looks massive and horrible. I wonder if it's just quartic here. Yeah, there we go. Stack exchange. Yep, converting to a depressed cortex, so you can make it, you can force this thing to lose a term. Expanding binomial powers, collecting same powers of u ends up with a u to the fourth plus u squared term plus a u term plus a constant term. So we drop out the u cubed term, and then we let all of these coefficients a, b, c result in this equation here. Yikes. Then using that, you use some of the same results that you had for other types of stuff before. So here, let y be a solution to the following cubic equation. And then all of this starts coming together. And we end up with yeah. This is just severely messy at this point. Yep, Ferrari ended up, Lodovico Ferrari ended up coming up with this particular version of a quartic. So he said let the u to the fourth term end up being a perfect square, u squared plus a, parentheses, squared. And we end up with a whole bunch of stuff. This is now a cubic equation, and Cardano was like, oh, that's not good. Because now you need the general cubic equation in order to solve the quartic equation. Damn. And so Cardano ended up breaking his promise and saying, Ferrari, you can use this particular solution to the cubic equation in order to solve your quartic equation. You need to be able to print this. You need to be able to publish this yourself. And Ferrari ended up, again, publishing the method that we see here. And Cardano got a nasty letter from Tartaglia that said that he was a plagiarist and a horrible person for stealing his work and ending up giving it to some no-named student. How dare he? So, Tartaglia and Cardano ended up having a bit of a falling out. And ended up having a bit of a falling out, as you can imagine. And Tartaglia then eventually lost his position and ended up retreating back to his home and retiring, because it just wasn't worth his time anymore. Yep, Gerolamo Cardano. Ars Ars Magna. Nope. And then people started working on the fifth degree polynomial and trying to find out why they were, or trying to find a general solution to the fifth degree polynomials. And as it turned out, it was not going to be possible ever. The general fifth degree polynomial doesn't work. It's not like the fourth degree polynomial where you can just bootstrap off of a third degree cubic in order to solve the quartic. In order to solve the quintic, you can't just use a quartic and then go off of that. It turned out that Évariste Galois, French mathematician, in the 1830s would end up showing that it was not possible. Yeah, Abel-Ruffini theorem in 1824, so pretty close to that same time. Proof this was the highest order general polynomial. Yeah, right. Proving that all attempts at solving the higher order polynomials would be futile. Then the question of why was something that Galois wrestled with, and eventually he came up with Galois theory, named after him because he was the first one to really end up coming up with it. And you can probably see right here, he died in a duel in 1832. He was trying to defend the honor of a woman in a pub because she had said something political, and then some other guy took offense and started yelling at her, so he stood up and said, "You can't do that." And then there was a fight, and the man challenged Galois to a duel, and Galois accepted and was promptly killed the next morning. The good news is that he left a copious amount of notes during the night in order to, leave behind some sort of copy of what was going on in his head, that his friends should be able to pick up where he left off. Right, so we're going to have to talk with higher degree polynomials about irrational and complex factoring, because that's fairly possible when you start looking into it. It is possible with the quadratics, but generally speaking, if you have something that is irrational, then you're using the quadratic formula to find it, and you're only going to get two solutions. They're both going to end up being irrational because you have a plus or minus a square root bit. In higher degree polynomials, it is possible that you could have a fifth degree polynomial and two of them are irrational. And so it'd be nice to be able to figure out approximately where those are. And then maybe figure out how to eliminate those. So factoring is also going to require long and synthetic division. Let's see. Solving equations and inequalities is going to be a thing. Alright guys, I'm going to call it there. Let's go over and see Dr. Gold at Actual Education. Those of you who are around, be sure to check out all of the other math streamers. We have Dawn Does Math, Zach at e to the 2i pi, Penn Center, Ian Stuckey, Obi, that's me, and Simplex Pachinko, Danny Highway, Dr. Gold at Actual Education, Merriweather Remark, Brian at Noble Penniless, Phobos, Dream, Physics and Depression, and XMDI0. We've got a number of other people who are really awesome and also teach math, so go check them out. A number of us have their other stuff. If you go to Penn Center's Discord, this is the Elements, and we have a Discord server where a number of us end up joining up and having a good chat about mathematics and place for you to drop any questions you might have. I hope to see you all on Wednesday. I'll be back for more. This is more of a math heavy stream, so we'll be doing more calculations and stuff like that. So, have a fun time. My name is Obi-Wan Pez. This is N Simplex Pachinko. See you later.